Reaction yields, or percent yield, tell us how well a chemical reaction went. It tells us how much product was made compared to how much product could have been made in theory. Usually when we go in the lab and do an experiment, we never make the amount of product that we could in theory. It's always a little bit less than what we would expect. The theoretical yield of a reaction is how much product should be able to be obtained if the reaction went to 100% completion. This is the maximum amount of product that we could expect. It's also the number that we get when we calculate from our stoichiometry our amounts of products. The actual yield of a reaction is what you get if you really go in the lab and you do the experiment. This has to be given to us in a problem, or it would have to be performed in the laboratory. We often describe our reactions as a percentage yield to describe how well it went, how much product was obtained. The percent yield is calculated by taking the actual yield, or the real yield, from the lab, and dividing by the theoretical yield, which comes from our calculations that we complete, and then multiplying by 100. The percent yield will usually be high, maybe 80 or 90% if the reaction went well and you got a lot of product out of it. Percentage yields could be very low if you could have in theory got a lot of product, but maybe you didn't because something went wrong. In a previous example, we looked at the reaction of calcium fluoride plus sulfuric acid forming calcium sulfate and hydrogen fluoride. We calculated the mass of the calcium sulfate that was produced, and we got about 6.9 grams. The amount that we calculated using stoichiometry, that was our theoretical yield that we calculated. Now if we're told that someone went into the lab and actually did this experiment for themselves, but they only got 5.3 grams of the calcium sulfate, we can describe how well this reaction went by calculating the percentage yield. The percent yield for any reaction can be calculated by taking the actual yield divided by the theoretical yield times 100. The actual yield is always going to be less than the theoretical yield because you can never get that 100% theoretical yield in real life. In this case, we would take our 5.3 grams that was actually obtained and divided by our 6.9 grams that we got from our stoichiometry calculation. Multiply by 100 to express it as a percentage, and this reaction would have had a 76.8% yield. This type of a calculation is often coupled onto the end of stoichiometry problems or limiting reactant problems to describe how well a reaction went. Let's try an example that combines everything we've learned so far. A chemist set up a synthesis of phosphorus trichloride by mixing 12 grams of phosphorus with 35 grams of chlorine gas and obtained 41.7 grams of solid phosphorus trichloride. Calculate the percentage yield of this compound. So in this example, we're going to have to do a few things. We're going to have to write a chemical equation and balance it. We're going to have to do a limiting reactant type problem as well because we're given the masses of both of our reactants. The 41.7 grams that we're told was obtained is going to be our actual yield because that's what someone got when they went and did this reaction. So from our limiting reactant problem, we will be able to figure out our theoretical yield. So first, let's write our chemical equation. We have phosphorus reacting with chlorine gas, and we got to remember that chlorine is one of our diatomic molecules, and our product we're forming is phosphorus trichloride, so that'll be PCl3. Balancing our reaction, we're going to have a 3 out in front of our chlorine, a 2 out in front of our PCl3, and then a 2 out in front of our phosphorus. So our mole ratios are 2 to 3 to 2. And now we're going to have to start with our 12 grams of phosphorus and figure out how much phosphorus trichloride could be formed if all of our phosphorus reacts. So starting with our 12 grams of phosphorus, we're first going to have to convert our grams of phosphorus into moles of phosphorus. And using the periodic table, we can see 1 mole of phosphorus is 30.9 grams. Then using our balanced equation, we can go from moles of phosphorus to moles of our product. Every 2 moles of phosphorus that react, 2 moles of PCl3 are formed. That comes from our balanced chemical equation and the coefficients out front. And then moles back to grams, 1 mole of our PCl3, if we were to calculate the molar mass of that compound, is 137.47 grams. Our grams of phosphorus will cancel, our moles of phosphorus cancel, moles of PCl3 cancel, and we're left in moles of our grams of our phosphorus trichloride. This stoichiometry calculation gives us 53.3 grams of PCl3, but remember, we don't know if that's how much product is formed yet, not until we check the amount that we could form if all of our chlorine gas reacted. So we need to set up a separate calculation to figure out how much product is formed if all chlorine reacts. So 35 grams of chlorine, which is Cl2. First, we're going to convert our grams into moles. 1 mole of Cl2 from the periodic table, if we take the atomic mass of chlorine and multiply it by 2, is 71 grams per mole. Using the balanced equation, 3 moles of chlorine react, and we form 2 moles of our product. And then lastly, moles back to grams using the same molar mass as before. 1 mole of PCl3 is 137.47 grams. Remember, if the molar masses are not given to you, you're going to have to calculate them. And if all the chlorine reacts, we should get that 45.2 grams of our PCl3 could be formed. So now we have to decide how much is actually going to be produced in this reaction. Remember, the lesser amount is the correct answer. So in this case, the 45.2 grams. That tells us that our phosphorus must have been our excess reactant, and our chlorine was our limiting reactant because it limited the amount of production of our product that we could make. So this 45.2 grams, this is our theoretical yield. That's how much phosphorus trichloride could be made in theory in a perfect world. Now calculating the percentage yield of this reaction, we need to take our actual yield, which was given to us in the problem, 41.7 grams, divide by our theoretical yield that we just calculated, 45.2 grams, and then multiply by 100. So our percentage yield for this reaction is rather high. It was 92.3%. When we talk about stoichiometry, so far we've been focusing on mass and moles. So we've been taking our grams of something, starting with the mass, and we've been using our molar mass to convert to moles of a substance, then using the balanced chemical equation to go over to moles of another substance, and then usually taking the molar mass and going back to the grams of something else, whether it's another product or another reactant, whatever the question was asking us for. We could also use density and couple in new calculations with this to talk about volume, since density is our link between mass and volume. And something we saw before was Avogadro's number, where we could figure out the number of particles. Those subatomic particles could be atoms or ions, they could be molecules. Avogadro's number was abbreviated with N sub A, and that was 6.02 times 10 to the 23rd particles per mole. But what we're going to focus on next in this chapter is a little bit of solution stoichiometry. And then later we'll look at some of the analytical techniques that can use different stoichiometry methods to calculate amounts of unknowns. So right now we're going to focus on this part of all of our different conversions, where we might know some volume of something, maybe it's in milliliters, for example, and we're going to convert to moles of that substance by using the molarity now. Whereas before we started with the mass and we needed to use the molar mass as our conversion factor. If we know a volume, we can use the molarity, which is moles per liter, to get at number of moles. Once we have number of moles, it's exactly the same as it was before. We can still use the balanced chemical equation in order to convert to moles of something else. And then depending upon what the question's asking for, we might be solving for an unknown molarity, or we might be using a second molarity in moles per liter to figure out an unknown volume of something. So looking at solution stoichiometry, it's very similar to the stoichiometry problems we saw, but instead of working with masses, now we'll be working with volumes and molarities. We'll still be needing our balanced chemical equations though to write the factors using the coefficients to go from a substance A to substance B. Here is an example of a solution stoichiometry problem. How many milliliters of 0.125 molar sodium carbonate are needed to react with 50 milliliters of 0.115 molar strontium sulfate solution? So notice we are given a concentration, 0.125 molar of our sodium carbonate, and we are given a volume, 50 milliliters, and a concentration of our strontium sulfate solution, 0.115 molar strontium sulfate. Our plan of attack to solve this is going to be that we're going to need to start with the volume of our solution and convert to our moles of one of our reactants by using the volume and the molarity together. So we're going to have to start with our strontium sulfate because that's the one that we know the volume and the concentration of. Then we can convert from moles of our reactant to moles of one of our other reactants, which is our sodium carbonate. And we're going to have to write a balanced equation to look at what the mole ratio is. And then lastly, we can use the molarity of our sodium carbonate in order to convert back to the volume of the sodium carbonate. So first, let's write our balanced chemical equation. We have sodium carbonate, Na2CO3, that's aqueous, plus our strontium sulfate, and that's also aqueous. And this would be a double replacement type reaction, so our products will be our strontium carbonate, and strontium is a +2 and carbonate is a -2, and our other product will be sodium sulfate, Na2SO4. And if we were to look at our solubility rules, our sodium sulfate would be aqueous and our strontium carbonate would end up being a solid precipitate. Most carbonates are insoluble. And if we look at the number of atoms on the left-hand side and on the right-hand side, everything already looks balanced. So that means that our coefficients out front are all going to be 1. Everything is in a 1-to-1 ratio in this balanced equation. And then let's take note. We have to start with, we know our volume and our molarity of our strontium sulfate. So we are going to have to use our molarity times our volume in liters to get at our number of moles. If you recall, everywhere you see a large M for molarity, you can cross that off and write moles per liter, because that's what molarity really is. It's how many moles of solute there are per liter of solution. So if we start with our 50 milliliters in units of liters, that would be 0.050 liters of our strontium sulfate solution. If we multiply by our concentration in molarity, 0.115 moles of strontium sulfate per liter, notice our liters are going to cancel, and that's how we get into moles of strontium sulfate. From here, we can use our balanced equation. Every 1 mole of strontium sulfate that reacts, it reacts with 1 mole of sodium carbonate. That allows us to move from moles of one species to moles of another. Our moles of strontium sulfate cancel at this point. And then lastly, we're trying to solve for a volume in this example. So we need to use our molarity of our sodium carbonate that was given to us in the problem, but we want our moles of sodium carbonate to cancel. Therefore, we're going to have to plug in the moles in the denominator, 0.125 moles per liter of solution. That way our moles of sodium carbonate cancel, and now we can convert our liters into milliliters. 1 liter is equal to 1,000 milliliters. So our liters cancel, and everything canceled but our volume in milliliters, which is what we were trying to get. Therefore, the milliliters that are required to react with the strontium sulfate are 46 milliliters of our sodium carbonate solution. Let's try another example. How many milliliters of 0.0475 molar phosphoric acid solution will be completely neutralized by 45 milliliters of 0.10 molar potassium hydroxide solution? And in this example, we are given our balanced equation already. So we have phosphoric acid reacting with potassium hydroxide to form water and potassium phosphate. Our phosphoric acid reacts 1 mole to every 3 moles of potassium hydroxide. We were told that our concentration of phosphoric acid is 0.0475 molar. Our potassium hydroxide is 0.100 molar. And we have 45 milliliters of our potassium hydroxide. So notice, for only one of the reactants are we given a concentration and a volume. That means we're going to start with the potassium hydroxide in order to get the moles. Once we have the moles of potassium hydroxide, we can work over to the phosphoric acid and figure out the volume required in milliliters. So starting with our volume of potassium hydroxide, we'll convert it to units of liters, 0.045 liters. Next, we need to multiply by the molarity, 0.100 moles of KOH per liter of solution. Our liters are going to cancel. Now we can use our balanced chemical equation. 3 moles of potassium hydroxide react with 1 mole of phosphoric acid according to the balanced equation. Now our moles of KOH will cancel. Right now, if we stopped and calculated, we would be in moles of phosphoric acid, but we want volume, so we need to use that molarity that was given to us. This is where we have to turn our molarity upside down, so it will cancel. We have 0.0475 moles of the phosphoric acid per liter of solution. So the liter goes on the top, the moles are in the denominator, they cancel. And then just because the problem asked for it in milliliters, we're going to multiply by 1,000 since there's 1,000 milliliters in a liter. Our liters will cancel. And our volume that would be required when we calculate should be 31.6 milliliters of the phosphoric acid. Quantitative analysis looks at different techniques in order to measure unknown amounts or concentrations of substances in samples. So 3 different types of calculations we'll learn about are titrations, gravimetric analysis, and then combustion analysis, which goes back to our empirical formulas that we saw in chapter 3. We're going to start with titrations. A titration is an analytical technique that's used in order to determine the concentration of an unknown solution. There's a little bit of terminology to understand before undertaking a titration. You have a burette that's usually filled with a solution that has a known concentration. You have a flask below that burette that contains the compound that has an unknown concentration. And in that flask is an indicator to let you know when your titration is over. The titrant is the solution that's the known concentration, which is what's inside of the burette. The analyte is what is inside of your Erlenmeyer flask, which is the unknown concentration that we're trying to determine. They also use an acid-base indicator. This is something that changes color when it goes from acidic to basic solution usually, and it allows us to know when to stop adding titrant from the burette and that our titration is over. If you take Chemistry 112, we will spend a lot of time talking about acids and bases in depth, and you will learn about the acid-base indicators and how they work. But basically, an acid-base indicator is something that changes color when it reaches a certain pH value. There's lots of different indicators with different names, and they change over different pH ranges. Often in this class, we use something called phenolphthalein. Phenolphthalein changes from colorless to pink in basic pHs, usually right around 8.3, but up to a pH of 10. It'll start as a very faint pink and eventually get to a hot magenta color. The first slight color of pink in a titration, if you're using phenolphthalein, would tell us that you've reached the end point and that you're done adding titrant. Since the indicator signals the end point of the reaction, we could then read the volume that was delivered from the burette and do calculations similar to the last two we performed in order to solve for an unknown molarity of our analyte. Let's try an example where we look at a titration and figure out what an unknown concentration is. Stomach acid is hydrochloric acid. A sample of stomach acid having a volume of 5 milliliters required 11 milliliters of potassium hydroxide solution for neutralization in the titration. What is the molar concentration of HCl? So in this example, we know 2 volumes and we know 1 molarity. We still first need to write a balanced chemical equation. We have a solution of stomach acid, which is an HCl solution, plus we're titrating it with potassium hydroxide in our burette. So the HCl is our analyte and the KOH is our titrant. Our products of an acid-base neutralization are going to be water plus a salt. The salt will be KCl in this case. And we have aqueous hydrochloric acid and aqueous potassium hydroxide since they're solutions. We know our concentration of KOH because that was in our burette, 0.0100 molar, and the titration required 11 milliliters of KOH. If you were doing this in the lab, that would be the volume that you read from the burette, however much you delivered. The amount that was in the Erlenmeyer flask of the HCl starting was 5 milliliters. What we don't know is we don't know the concentration of that HCl. So when we decide where we have to start, just like last time, we only have one species that we have a concentration and a volume for. That's the spot where we need to begin our calculation. We're going to start with our 11 milliliters of our potassium hydroxide. We want to convert that to liters. So that's going to be 0.011 liters. Next, we're going to multiply by our concentration, 0.0100 moles per liter, and that's of our potassium hydroxide, so moles of KOH. And from our balanced chemical equation, the KOH and the HCl react in a 1-to-1 ratio. So for every 1 mole of KOH that reacts, it reacts with 1 mole of HCl. And this is where our problem gets a little bit different than the last two examples that we saw. Last time we were trying to calculate a volume, but now we're trying to get a molarity. Remember, the units of molarity are moles per liter. So we just need to have units of moles of HCl over liters. Our liters of KOH cancel. Our moles of KOH cancel. Right now in our numerator, we have moles of HCl. So our final step is just going to be to divide by our volume of solution in liters. We knew that we started with 5 milliliters of our HCl solution. So we can write that as liters and divide by that. We're going to have 0.005 liters of our HCl solution. Now our units will be moles over liters when we divide. Our unknown concentration of the HCl was determined to be 0.022 molar HCl, or we can write the units as 0.022 moles per liter. Either one of those is acceptable. So a titration's purpose is to figure out what that unknown concentration is. Sometimes if an approximate concentration is known, before a titration is done, a quick calculation can be completed to see about how many milliliters will be needed from the burette in order to titrate. This would let you know when to slow down on your titration, since you would usually have to go drop by drop. How many milliliters of a 0.211 molar HCl solution are needed to titrate 275 milliliters of a 0.035 molar barium hydroxide solution? So first, since we're not given an equation, we have to write one and balance it. We have aqueous hydrochloric acid reacting with aqueous barium hydroxide. And this is going to be a double replacement. So our products are going to be barium chloride. Barium's a +2 and chloride is a -1. That's going to be our salt, and we're going to form water as our other product. We're going to have to balance this. We're going to need a 2 out in front of the HCl, and then we're also going to need a 2 out in front of the H2O. So now we can see that our HCl, 2 moles of HCl will react with every 1 mole of barium hydroxide. We have our concentration of our hydrochloric acid, 0.211 molar. Our concentration of our barium hydroxide, 0.0350 molar. And we know our volume of barium hydroxide, 275 milliliters. That would be our analyte in this case, and we would be titrating with the HCl inside of the burette in this example. So we're going to start with our barium hydroxide and work backwards to our HCl to figure out what that unknown volume is. So starting with our volume in liters of our barium hydroxide, we're going to have 0.275 liters, and we're going to multiply by the molarity of that solution, 0.0350 moles of barium hydroxide per liter. Now going from moles of barium hydroxide to moles of HCl, for every 1 mole of barium hydroxide, 2 moles of HCl react. And then lastly, using our concentration of HCl to get at volume. Our concentration is 0.211 moles per liter, so our moles of HCl will go in the denominator. Our volume will go in the numerator. And in our last step, we will convert our liters to milliliters. We'll check and make sure everything cancels. Our liters of barium hydroxide, our moles of barium hydroxide, moles of HCl, and liters of HCl. So when we calculate, our volume required of the HCl should be 91.2 milliliters for that titration. And when we titrate with 91.2 milliliters, that would be the exact amount required for complete neutralization, meaning that neither one is our excess reactant and neither one is our limiting reactant in this case. We're calculating the perfect stoichiometric amount required for complete neutralization so that our only 2 products left at the end are the barium chloride and the water. That's been the underlying assumption in all of these solution examples. You could possibly see problems where they give you a molarity and a volume of both of the reactants, and then that would also be a limiting reactant problem as well.